Well, good afternoon, everyone. This is about quadratic functions, and the primary teachers may think, well, there's not much we teach about quadratic functions in primary school, but it's very, very important that you do, but not the formal stuff with equations, but the really important ideas that the vocabulary that the young learners need to learn if they're to be able to do the mathematics once they're in secondary school. So yes, it's important that they start really from foundation level, talking about some of these ideas. And you'll see when you see the what we're doing, why we're saying that. And I'm Tony, and I started AIMSEC just over 20 years ago now.
Hello, everyone. My name's Caroline Ainsley. I'm the founder of Bubbly Maths, and my purpose in life is that every child on earth will love learning and enjoy mathematics. And what better way to do that than work with Tony, helping teachers find more interesting ways and more engaging ways of learning mathematics.
Sam is in Kenya, and I think he must be having some difficulties this afternoon.
Hi everyone, I'm Lucian Talu. I'm from African Maths Initiative. We work with Sam Okoth. So African Maths Initiative deals with a number of projects. So I'm part of the education team. So far we are concerned with Math Club, Math Camps, Happy Classroom Project, Math Competition, and so on.
Now the program today is about not just quadratic functions, but equations and their graphs and ups and downs. You'll see why I'm saying that in a minute. Now, we believe that learning starts with early years, even before the children start school, and the foundation is built there for later learning. And the path is like a spiral staircase where you go up and round and round and up and round again. And in each level, the children are learning a bit more, and ideas that they have met when they were younger, and they need to have met when they were younger, they meet again. And when they meet it for a second time, they're able to build on what they know and learn a bit more, deepen their understanding. And each time at a higher level that they meet the same topic, they learn a bit more about it. Now, today we're going to improve skills, knowledge, and understanding of functions and their graphs, of quadratic functions, of quadratic equations, and transformations of graphs and applications in sport and designing and firing missiles, and applications in telescopes and satellites. And as always, we're going to start off with what you might do with very young children in the reception in grade 1, and then as they grow older, more things that you can do with young children and working up from that. So that's why we've got 1 at the bottom as we're climbing this spiral up and up and up, and relearning basing what we're learning on what we've learned in the past. So we're going to notice some flight paths of objects in sports and in firing missiles. We're going to do a workout. We're going to do some physical exercise. We're going to look at conic sections. We're going to look at telescopes and searchlights and how they work. And then only much later will we come to these quadratic functions and their graphs, and matching the graphs to their equations and transformations of graphs. And then we'll look at the flight path of a projectile. If you throw a ball in the air, it goes up and in an arc and then lands again. That's a parabola. The shape that it makes in the air is called a parabola. And then we'll come to review the workshop.
As with all our sessions, during this session, we'd like you to think about wearing 2 hats. One is do the activities as though you were a learner, as though you were one of your learners. Think about how your learners would do them and what problems they might encounter or what questions they might have. But also reflect as a teacher on what they could learn and how you can guide their learning. So Tony mentioned ups and downs. We're looking at the flight paths. We're looking, in this case, that's all about balls being thrown in the air, being kicked in the air, being whacked in the air by a golf club or a stick and a tennis racket. And it's all about reflecting on the path. So what the questions you would ask your learners is, one, you could answer this in the chat. What do you notice in the pictures about the flight path of the balls? Imagine what's going to happen to the ball. Like the tennis player hasn't hit that ball yet. What is going to happen? The basketball player hasn't released the ball yet. What path is the ball going to take? And it's at any angle. Does it matter what angle it's thrown at?
So there's plenty of opportunity here for talking about the pictures. And what you could do, if there's two people in the room, if you've got a small object like an eraser, you could throw it in the just up to the other for the other person to catch and watch it as it flies through the air. And hopefully the other person will catch it, and you can both look at it and see what path it travels through the air between the two of you. And you can get the learners to do this in the classroom. Well, just two learners. You don't want everybody throwing things. Or you could do it in the playground. Now, we call this a projectile. The thing that flies through the air is called a projectile. Now, the little boy there is shooting an arrow. This projectile could be an arrow. It could be a football. And the lady in the middle, she's putting the shot. She's got that ball just by her neck, and she's going to lean back and swing her arm right round. And they call it putting the shot. Actually, it's throwing it with a good deal of force. And if you watch the shot in the air, it'll take the same shape. The flight path will take the same shape as the ones we saw marked from the cricket ball and the golf ball. And then a high jump. Now that person's doing a high jump, and their whole body will curve as it goes over the bar, and it will go around the shape of that curve, the same sort of curve as we've been looking at in the other pictures. And there's plenty for young people to talk about in these pictures, and for you to you help them develop the vocabulary. Now, this one is again called Ups and Downs of Projectiles and Quadratics. Now, the curves you see in this picture have been designed for safety in the case of the roller coasters and the slides, the water slide, and even the skateboard park, so that as the car on the roller coaster comes down, it's not going to go too fast and shoot off, and it's not going to be an accident with it. Those curves are not all parabolas, but they're very carefully designed. And so, as you see there, the picture of the one that's in black and white, that's entitled 17th Century Warfare. You see in the distance there's a town, and the soldiers in the foreground are firing a cannonball to land in the town. And the path again is a parabola. We'll talk about it, and we'll see why that's the case later on. So these people, and nowadays with weaponry, it's just the same and just as brutal and horrible. Weaponry is designed to hit its target accurately, and there's a lot of maths that's used and calculations that go on so that it is fired with precision. But nowadays, those calculations are done by computers. But in Europe, in the past, a few hundred years ago, people used to build high walls around their cities, and they were very rich, they might build a castle and with a wall around it, so that if anybody attacked them, the wall would protect them, but the attackers would have to fire their shots over the wall.
I just wanted to emphasize that most of these designs are either for safety or for accuracy, to avoid hitting something that is out of target, or maybe, for example, the skateboard park is mostly designed for safety of the skaters.
We see the same pictures again, and with your class, even 6-year-olds, you can talk about the ups and downs of these rides on water slides and in the playground. And the children should look at the pictures and describe the rides from start to finish. What do they see? And what are the similarities in the shapes of these slides and roller coasters? And what are the differences? Does a ride usually start at the top or at the bottom? And is there a difference between a water slide and a roller coaster? Well, what is it if there is a difference? And is it exciting to climb steeply or drop suddenly? Now, those water slides are actually in Musenberg, where the AIMSEC office is located. But everybody, even if they've never seen slides like that, or the roller coasters, they walk up and down stairs, and they're used to walking up and down hills. That's part of everyday experience. So although they might not have experienced rides like this, the discussion introduces ideas of curves and, very importantly, of steepness. So this curve going up steeply or not so steeply, going up steeply or not so steeply. And they're important concepts in mathematics. And this discussion will help children to develop a vocabulary about curves and movement on curved tracks and up hills and down the other side and into the valley. And they'll use that later in describing graphs.
So it's not only about graphs, we're talking about curves and gradients, and we're going to look at some physical sciences here. This is a great activity to do with younger learners, so this is aimed at primary school teachers predominantly, but even in secondary, you can be looking at material sciences, definitely testing what happens if you adjust gradients, and that sort of thing, and the shape of the curve can also matter. You test different materials. Let a car go, let a marble go. You can do timings. There's a lot of activities you can do in secondary, quite to a greater level of precision. And in primary, it's simply experiencing it. But again, that you see the idea of actually creating a ramp using plates and doing and being, you can be super creative with that. But also you can use different materials. So is it going to be the same if you cover the ramp in carpet? What is going to happen? Why is that happening? You can add friction to the equation. You could maybe make something with sand and something else with smooth metal, even just a tray, cover it in sand, and a tray covered in smooth metal. You can just do lots and lots of experiments.
So one thing you can do is to get the learners, help everybody to make a marble run or run a toy car down the run, and be creative and use different materials. And you could have this as a group project, and each group of 6 or 8 learners have a limited time, not to spend a lot of time on it, but to make their own ramps. And then when the marble or the car runs off the bottom and then goes along the flat surface, how far does it go? And they could time the distance, because later on we're going to do some work on equations of motion and look at the distance. So a moving object goes in a certain amount of time, and your learners could time how long it takes for the marble or car to travel down the ramp from according to the height from which you drop it and how far it goes when it runs off the bottom. And then, as Caroline says, if the surfaces are different, if it's running on a carpet or a smooth surface, does that make a difference to how far the marble or the car goes? And why? Ask the question, why do you think it makes a difference? Bring in the idea of friction. So Caroline's now, we're going to do a workout, some physical exercise, and Caroline's going to demonstrate. And we're going to talk about which graphs the stickmen demonstrate and how and why the arm positions show different lines and what the equations might be. When you do it in the class, in a lesson, you'll need to have your back to the learners, so they do exactly what you do, and that's why Caroline's turned her back to us. Now, we'll just start with little stickman A, who's doing the graph of y equals x. Okay, and what we imagine is that where the stickman's arms join his body, that's the origin. That's the point 0, 0, and that the y-axis is straight up and down through that point, through the top of the head and right through the center of the body. And the x-axis, put your arms along your x-axis, Caroline. The x-axis is with her arms horizontal, and the y-axis is up through the top of Caroline's head and right through the center of her body. And it will be the same for you. So you carry your own x-axis and y-axis around. Now, the first equation is equation A, where, well, little stick person A, y equals x. Right? And now the second one is y equals minus x. Now we're suggesting that you stand up and do this as well. Y equals 2x.
2x.
Oh, okay. So, so what Caroline is showing us is a steeper line. Okay. So the angle is at 60 degrees with the x-axis now. Okay. That's right. Sam's doing it too. Y equals 2x. And now y equals minus 2x. Okay. Now what your arms should be through with the x values negative with your right arm and with your y values positive with your left arm. Okay, so that's y equals 2x. And now y equals minus 2x. So do it again, Caroline. Y equals plus 2x, 60 degrees, y equals minus 2x. Well, that's great. Okay, now then, we'll go on to y equals minus x, right? And what now? Y equals minus x plus 3. And she's standing on tiptoes. She can't balance her because she's not a ballerina, but she's raising the graph up. Okay, now this is easier, Caroline. Why now you've got to do y equals minus x.
Easy for you to say.
Minus x again, and y equals minus x minus 2. So this is easier because she's crouching down, okay? And now, Caroline, y equals minus 2x minus 2.
Minus 2x minus 2.
Right? Well, Caroline, your body has to be straight because your body is the y-axis.
As I said, easy for you to say.
So sorry. But yeah, if all your learners end up laughing, so much the better, because it's just meant to be fun. And
you'll end up with sore thighs.
Children have a lot of energy, and this is one way that they can use their energy productively. For a challenge, you could try y equals 2. So that one, you put your arms out horizontally and you just go up a bit, 2 units up. This one, it doesn't matter whether you've got your back or your, or really, you can imagine it either way. And x equals 2 is much more difficult because we defined the origin to be where your arms join your body, or right in your middle of your body there.
Okay, well, let's give it a go, because it'll be fun in class. Kids absolutely love doing this. So if that's x equals 0, and then x equals 2. So if I go in the correct direction, they kind of scooch over a bit.
The problem is you're carrying your y-axis with you, so you can't do that one.
No, my
perfectly.
my y-axis is here.
Oh, your y-axis is okay. Okay, so it's all a matter of whether your y-axis is in the room, or whether you're carrying it with you. And everybody in this when the class are doing this, everybody's got to imagine their own y-axis is through their own body and moves with their body, and their x-axis is well, no, it's a line through their body in the room, and the x-axis is where their arms are straight out. Okay, and x plus y equals 3 is one to think about. X plus y equals 3. If I was doing it with a class, whether it was primary or secondary, I would show them, we would talk about doing this and do a few together with me demonstrating, but then I get the learners to come up and do the demonstrations.
Shall we continue with the workout this time around, the modulus function? And the fun part is that I don't need to spotlight myself. There is already demonstration of workouts of how we can be able to show the modulus for y is equal to mod x, and then next and next. I will tell you something interesting about where I am at the moment. It is very cold. So if I stand and stretch like this while demonstrating, that is when I can get warmth. So this is the first, if you look at the first picture, shall we do together? Yes. And then the middle, and then the last one, like this.
And they probably won't learn about the modulus function until about year 10 in school, but it's an important function in mathematics, and we're doing it with you as teachers because the teachers should know about it, really. And the arms have got to be straight here, and that's the modulus function. What about this one? Now, this one is our quadratic function, the parabola. And here, the arms are nicely curved around, okay? And that's y equals x squared. And then if we bring our arms together steeper, y equals 2x squared, okay? Then we're making a steeper graph, that's y equals 2x squared. Spreading our arms out, not such a steep curve, that is y equals a half x squared.
One interesting one that is the last one, the equation of a circle where around the head was the midpoint. And if you try it like this, negative x cubed, and y is equal to x cubed, this way. Owen is saying that my elbows for the last should be round. My elbows for the I've tried to make it as round as.
It's really difficult to get your arms in this curve. Okay, so we're coming on to something where we make some cuts in 3 dimensions.
So in primary school, I found that one of the favorite shapes is a cone. They see a pyramid, they say it's a cone. They see different things. Oh, it's a cone. They get excited about cones.
Ice cream cones, of course.
Ice cream cones, yeah, not so easy to find in Kenya and South Africa maybe, but not so easy to find in Kenya because they melt. But what if you make a cone, which is really easy to make, you're just using a piece of A4 paper or some used card, then you find if you slice it in certain ways, you make other shapes. So if you slice it horizontally, you make a circle parallel to the base. If you slice it diagonally, just anywhere diagonally that isn't a circle, you will make an ellipse. And then if you go down to the base, if you get down to the base and you slice it, and you're slicing parallel to the opposite edge. So if you've got the edge going up like the side of a mountain and just make a slice following that same line, you will have a parabola, the same curve as you have when you throw a ball in the air or any projectile in the air. And then finally, the hyperbola is if you are making a slice that's perpendicular to the base. So that's a nice way of introducing the word perpendicular or using the word perpendicular. They can actually make this because it's got to be at 90 degrees to the base. And that's a nice way of them really solidifying their understanding of the word perpendicular, or one of the many ways that you can put that word into practical use. And the curve that you make, if you have a curve that's sliced perpendicular to the base, will be a hyperbola. It's magical. Maths isn't, to me, maths isn't magic because it's not, there's no actual mystery involved in it. It's just magical. These amazing things come out of a cone.
It's awesome. To make a cone, you take a sector of a circle and glue the straight edges together. When a parabola is rotated about its axis of symmetry, then you get a bowl-shaped surface, as you see the coloured surface in the diagram here. This is called a paraboloid. So if the paraboloid, the inside of the surface, is a mirror, then this will give you a telescope. The rays of light, a parallel beam of light, hitting the telescope, hitting this mirror inside the paraboloid. All those rays bounce off the mirror, are reflected off the mirror, and they all get focused on a single point called the focal point. The parabola is a unique shape that has a focus like this, and here you'll see it used for a telescope. But you could reverse that. You could put a light source at the focal point, and then the light would shine out from there, and the rays of light that hit the mirror surface would bounce off as a parallel beam. And on the right here, the little picture, you see it looks like a wartime picture, and that's quite a strong beam shining from the searchlight there. Now, stretching the parabola horizontally and rotating it about the axis again, you get a parabola that will reflect wider beams of light, suitable for different searchlights and telescopes. So if you make the parabola, if you stretch it to make it wider and shallower, then you will get a wider beam of light that can come into your telescope or be sent out from your searchlight.
So Tony and I, mainly Tony, I have to confess, we've been working very hard on a book. This book has got 36 games in it, and the reason why we're telling you about it is it's going to be out in March, and there will be a special price for people buying it in Africa, because it's a book that's it's aiming high family games. there will also be a teacher's book and a classroom book to follow. It's an AIMSEC publication. So all the activities that Tony puts on the AIMSEC page every day on Facebook, not all of them, but a lot of those activities have been made into really clearly explained games. And all of these games are there to help develop the love of maths, to improve numeracy, visualization. There's many games in there that do your drill and practice, but do it in a fun way where the learners are quite happy to do it, more than happy to do it. And they improve their numeracy, and lots of visualization activities, and it just generally concentration, visualization, critical thinking, decision making, strategies, and in general boosting confidence in mathematical activities. This book will be out in March, hopefully March. We hope March, because it's the 20th anniversary of AIMS in March, and there'll be big celebrations of that. So and in March also, this workshop, the GTEN workshop, will be based on playing some of those games. And there's also a family games kit which you can get alongside it with all the bits to play. But as usual with anything that we do with GTEN and Aiming High, there are ways of doing it using scrap. So all the pieces that you need can be created using scrap materials.
But we've put these games together so that there are games for all ages. So there are 36 different games, but each one comes in a few variations of the game, simpler variations if you've got young children, and more challenging variations for the older members of or older classes in school, or older members of the family. And for people learning the games, they play the simple ones and gradually work up towards the more challenging games. So there are 36 sets of games, if you like, and they're all going to be on the Aiming High website.
Yeah.
And I'm working on that to complete notes for teachers there, and there's lots of interesting questions about these games, a bit of the history of the games. And one of the things that Caroline hasn't said is that we're offering a copy of the book as a prize, or several copies of the book as prizes if we get lots of people entering this competition, and it won't cost you anything to enter it. So there's also packs of playing cards with mathematical games as well. So we're going to give some of these as prizes to teachers who play the games either with their families or with the learners they teach, and report about it and say, what features of the game they like and what they might do to improve the game. Because in a lot of cases, we have suggested that you can change the rules. You can play our game, or you can be creative and change the rules a little bit and play your own version of the game. So what we're suggesting is that if you go to Aiming High, you will find the games, and there will be a mention of this prize, and just look for games on Aiming High. And if you join the conversations and chat on Aiming High about the games, we'll see who's got most involved, and we'll be giving you a book for free. Now, for everybody, these games are designed for teachers in Africa, in the schools where there aren't many resources and there isn't much money for buying books. So there will be an e-book. So you're going to do an activity in a few minutes where you'll be matching cards, and this is an example to show you what you'll be doing. Here you see a quadratic equation, ax squared plus bx plus c, and its corresponding graph. And if you look at the example, a is -2 because you've got -2x squared, b is 11, and C is -5. Now the corresponding graph cuts the axis at 2 points. When we try to see what those points are, we notice that the points 2, 4 and 6 are marked on the x-axis, and the points where y equals 0, giving the solutions of the equation, are at the point x is 1/2 and x equals 5. Now, the first thing you do when you have to solve a quadratic equation is you try and see if you can find the factors. And here there are factors, not very easy to find, but if you look at it, you'll see that the factors are 2x minus 1 multiplied by 5 minus x. The product of those two factors equals 0. So to get the solutions, one or other of the factors must be 0. If the first factor is 0, then x is 1/2. And if the second, in the second bracket, 5 minus x is 0, then x is 5. And that gives you the two solutions. I'm going to introduce you to the first task, this first matching exercise, and we're going to give you plenty of time to do this. On the left, you'll see 5 graphs, 6 graphs, 7 graphs even. You'll see 7 graphs, and they are labeled G1, G2, and up to G7. And there's a space there, and we would like you to sketch the graph of y equals x squared. So that's like the other graphs, but it goes through different points, okay? And on the right, you'll see there are 14 cards there. There are the y cards, which give you the points where the graphs cut the y-axis, and the x cards were giving the points where the graphs cut the x-axis. Now, for learners, we would cut out all these cards and match them. But for you, what we're suggesting is that you look at them carefully and you match the cards. Each G card matches with an X card and a Y card, as in the example that Sam showed you. For example, if you see the G1 card, it cuts the x-axis at the points 2 and 8, and it cuts the y-axis, we've given that to you, at the point where x equals 0 and y equals 16. So the G1 card matches with the x5 card here, which gives you x equals 2 or 8 when y equals 0, and we've given you the y card that it matches. They're not very well to scale, so to make it easy, we've just given you the y cards, and what I want you to do now is take your time and match the the graphs to the x cards and fill them in this empty column on the right. And also, don't forget, sketch the graph of y equals x squared. We put some axes in and the graph of y equals x squared. Caroline showed you that she was doing this with cards that she'd cut out, and learners should do this by sorting actual cards, and you'll find the cards on the Aiming High website. So Caroline's going to talk about this next exercise, which will be easier.
This time, instead of matching the coordinates, we're going to match the polynomial form and the factorised form.
Now remember that it's where x equals 0 that you get the point on the y-axis. So you should be able to look at the point on the y-axis, and that should help you to find which of the A graphs they are. and you put y equals 0 to get the points on the x-axis, and there it's where x makes what's in one bracket or the other equal to 0. This is great as work for people to do in pairs, for your learners to do in pairs, so they can help each other and check each other. So that that's how I'd do it in class anyway. Given all the solutions there, and you can all check them. In South Africa, this is a time when learners are doing exams and tests, and this is a good revision exercise for the learners to do this card matching. Talking now about grade 10 and 11 learners, they will have all learnt all this, and this is a good way for them to revise for a test and help each other to get it all right.
Just to have a look at what we have achieved so far on matching the quadratics, from the intercepts with the axes, and just what we've looked at right now. You can be able to see all the graphs, how the lines cut at the y-axis and the x-axis, and how we can be able to match. So for example, you can be able to see G7, A1, B7, Y1, X7.
So let's move on to transformations of graphs. And here, and with all this work, you can draw these graphs with GeoGebra, free software, if you've got it. And in GeoGebra, you can see what happens as you change the values of the constants. Here, we've got A as the, it's giving you the translations, and the stretches are given by K here in these graphs. So if we look at the first one, which is y is f of x plus a, whatever the graph of f of x is, adding a plus a will move it up in the y direction. So the what is drawn there as a black graph goes up to be to give the red graph, and the black graph is y equals x squared. And if you've got the function x minus a, it works for all functions, but here we show it for the black graph y equals x squared. And here it's shifted to the right, and it's opposite to what you might think, perhaps. Now, what about a reflection? If in the middle there, the reflection is given by taking your function and putting a minus sign in front of it, and that reflects the y equals x squared, which is the black graph there, to give the red graph. That's given by changing the function y equals fx to the function y equals minus fx. And then this is one of the ones that Sam talked about in the workout. This one is y equals x cubed in black. And so the function we've illustrated here is y equals x cubed. And here, if it's reflected in the y-axis to give y equals minus x cubed, we change the fx to f of minus x there. So wherever we had an x before, we put a minus x now. Now, another of these transformations is to stretch the graph. So if you look at the curve there, not only is it shifted a little bit to the right, if you see it as a sine graph, which it looks like, but it's moved a bit to the right, but it's stretched up. So you have got a stretch by a factor k in the y direction. And the next one, the next graph is stretched by a factor 1 over k, which is, so you've seen there in the illustration, the black graph, how it gets changed to give the red graph, and it's sort of squeezed in the x direction. When you change, where you had x before, you put kx, so that instead of f of x, we've got f of kx. So that is just a little bit of chat from me, but I know that this is something that is very much part of the year 11 work in South Africa. But what I'm introduced it here, because if you link it in with this next graph, then it makes a lot of sense. This brings everything together. So if you think of the quadratic formula for the solution of a quadratic equation. So if you see the graph here, this is the graph of the y equals ax squared plus bx plus c, which is the general graph. As you change a, b, and c, you get different parabolas there. And the 2 points where it cuts the x-axis, I think you all know this formula, that x is minus b plus or minus the square root of b squared minus 4ac over 2a, give you the two solutions, and they're the two of the quadratic equation, where y is naught, and they give you one on the left of the origin and one on the right of the origin in this diagram. And if you put x is naught, you're only left with y equals c, and you see that point on the y-axis there. But this graph also has an axis of symmetry. Now, all the graphs of quadratic functions, absolutely all of them, are transformations of that parent graph y equals x squared. Now, it has an axis of symmetry, which when we were doing the workout was we took to be our body, right through the center of our body, vertically up and down. And here, that axis of symmetry is translated by a distance x as minus b over 2a. And that's where the minus b over 2a, it corresponds to the first part of the quadratic formula that gives you the solutions there. So what is happening here is that you have everything that you teach the learners about when you teach them to solve quadratic equations by factorizing or by using the formula, when you teach them about the graphs, how to just draw the graphs. Originally, when they first learned by plotting points, and then they ought to be able to sketch the graphs just from its features, like the critical points. And then you'd also teach about transformations of graphs. And to find out about those transformations, you can look at the equation in a different form. Here it's a times x plus p all squared plus q. And as you change a, p, and q, so you change the graph. And you can do that easily and actually watch it as a moving demonstration in GeoGebra. So what we have here is we're looking at a point moving, and the horizontal distance traveled is x, and the vertical distance traveled is y, and that might be a ball that's just been thrown or hit with a tennis racket, and g is the constant of acceleration vertically downwards due to gravity. Now, if that ball starts with a horizontal velocity of u meters per second, at the beginning, that's the initial velocity, and a vertical velocity of v meters per second when the ball is projected, then the x coordinate is given by equation 1 there, x is ut, and the y coordinate is given by y equals vt minus a half gt squared, or the y distance move, the distance up or down. At any given time t, those equations give you the position of the point. Now, we all know that distance is velocity times time. So the distance is x, is the horizontal velocity, u times the time. And we've got the equation for y there. Now, differentiation gives us a rate of change. And if we find the rate of change of distance, that will give us the velocity. So what I want you to do is to just write down, I won't give you very long for this, but just write down the derivatives of those two equations 1 and 2. Differentiate dx dt and dy dt, and they will give you the velocities, because that will give you the rates of change. But because some of you haven't done any calculus, I'm going to give you the answers. And those of you who do know calculus, you can just check that I've got it right there. Now, the rate of change of velocity, when you speed up, when you put your foot down on the pedal in the car, the rate of change of velocity is called acceleration. So if we now differentiate again to get the acceleration, what do we get? We want a horizontal acceleration, which is the second derivative, d2x dt squared, and we want a vertical acceleration, the second derivative, d2y dt squared. Okay, so if you know about differentiation, you can see that when we differentiate the constant, we get naught, and that's because it ties in with what we know, that there's no horizontal acceleration. There's nothing to make the ball move horizontally, but there is certainly something that changes its path, and that's gravity, and that's vertically downwards. So we see that the acceleration is minus g. It's an acceleration constant g downwards due to gravity. And so now you see how the calculus that you teach ties in with the physical science and these equations of motion. If the learners are doing physical science, it will all fit in, like all be different ways of looking at the same ideas.
So now we're going to look at the path, the trajectory, the parabola that we've been talking about from the beginning. And now we're going to use algebra. So we're not talking about rate of change. We're just looking at algebra. So whether you've seen this or not, all you need is algebra. Have I said that before? So X and Y are the horizontal and vertical distances. So we'll imagine the parabola we've been looking at. X and Y are the horizontal and vertical distances, and G is the constant acceleration vertically that's pulling it vertically downwards caused by gravity. So we're going to start at an initial velocity, which is going to be u, meters per second. And so at any given time t, any time at all, no matter what t is, x, the x coordinate, wherever it stands in the graph, is u times t. So the initial velocity times the time. Now the initial vertical velocity is v meters per second. So that's upwards. And the y coordinate, and these are given by Newton's laws of motion, is vt, so the vertical velocity times the time, minus half the acceleration due to gravity times t squared. We've got these two equations, so using those, all we have to do, we've got super simple substitution for t, so we can work out t using the first formula. And what we want you to do is go ahead and do that, please. Work out what is t from formula 1, and then work out y by substitution. So here we have it. There's the first two equations, and substituting and just rearranging formula 1, you've got t equals x over u, initial velocity, and then by substituting into equation 2, you've got that equation there, which I won't spell out. And then that is a quadratic equation. So y equals a constant times x squared plus a constant times x plus constant c. So in this instance, constant a is negative g divided by 2u squared. Constant b is v divided by u, so vertical velocity divided by horizontal velocity, and c is 0. And that is a parabola, equation of a parabola.
So we've seen a lot of connections here, of one bit of maths with another bit of maths with another bit of maths that our learners have to learn. And what you see here is the time is actually a very important part of the whole consideration of where the particles is at a particular time. But if we just want to look at the path, we want to what we say is eliminate t to get y in terms of x, and we can see how the equation of the path, the flight path. And the other word that's used there is trajectory. Sometimes that is used to describe the flight path. So we've come to the point where we look back at what we've been doing. We see the different things we have studied this afternoon together and think about what we've done.
Actually, I wanted to bring in an idea of one of these can be simulated. So this is a simulation from Fayette, Colorado, and on projectile motion. And I wanted us to simulate one of the examples that we were doing practically. So you can set this to any angle. You can play around with any of the parameters that are here, but I wanted us to just try out something and see what we were doing practically. If you can't be able to see that.
We can see it, Sam. It's great. It's good.
And
Yes.
you can even see all the points that have been plotted to achieve it.
Yes.
I love the people maths doing the graphs. I think that's a great way to really get the ideas solidly in your head. And for me, the cone, I've always been fascinated. And I love the fact that those curves naturally occur in a cone, and it's part of the mathematics of the cone.
What I really like about this is the way everything connects with everything else. You know, the common theme, the sort of, you know, the thread that ties everything together is that parabola, that path of the ball in the air. And I like the way in which everything, the calculus, the algebra, the pictures, everything ties in with everything else and connects up. And it is a good lesson for teachers, really, that when you're teaching, to help the learners to make those connections, because it helps them to understand the maths much better and remember it too. And it, of course, not only connects with other topics they learn about in maths, but for those who do physical science, they learn about it there. And then there's the design technology, isn't there? Making the marble run and linking that with equations of motion and ideas that they will come across in physical science, like friction and other things like that. So on the Aiming High website, you've got lots of what we call learning packs. Everything's freely downloadable. You've got worksheets. You've got the Inclusion and Home Learning Guide. And what's special about those is there's activities for all ages, for small children, 6-year-olds, and right up to school leavers. And the notes for teachers come with solutions and key questions that you can ask in the classroom. And if you want to do some formative assessment, there's always a diagnostic quiz.
And the links that you'll find helpful, we have our YouTube channel, which is called Maths Toys. There's daily activities, a daily lesson starter, daily activity on the Facebook AIMSEC SA Facebook page. And then you can watch our workshops live. So what you've just seen, You can watch live, just email admin@aimsec.ac.za to be added to the WhatsApp group, and you will be part of the conversation and get the links and the dates and times every month. The other contact information, you can look up, see what AIMSEC's doing, find out more about AIMSEC and the Aiming High activities. Contact Tony and myself with those email addresses. Contact the AIMSEC team if you want to sign up for one of the AIMSEC courses as a self-funding student.
So it's time to say goodbye. We hope you'll join our future workshops, and we'll see you in the future.
We will. Thank you, and see you next time.